Welcome back to 8701. So in this video, we talk about stability and the opposite of stability, the decays of nuclei. Okay, so let's look at this diagram first, which shows the number of protons and the number of neutrons here. And you find that the stable elements sit in the so-called valley of stability. So there's a certain part of our nuclei which are stable. This valley follows directly out of the discussion of the binding energy, where you can calculate the optimal Z value such that the mass is minimal. It's about a half in this area here at low masses and about 40% of A in the higher part at high value of mass. We already discussed that the binding energy has this form here with a maximum around the mass of iron. Should be more precise, somewhere here, 50 some. Okay, so it's energetically favorable for some unstable nuclei to just break apart in so-called fission processes, and it's also energetically favorable to fuse together to create energy. And we'll talk about the applications of those processes later on. But for now, we want to just look at radioactive nuclide, which can decay in various ways. And so the first most prominent decays we want to discuss here, and then we'll follow up a little later, is the alpha decay, which is splitting up a mother particle splits up into a daughter particle nuclei and a helium, which is an alpha particle, or the emission of electrons, positrons, or the capture of electrons as well. It is also possible, but rather rare, that a nuclei just spits out a proton or spits out a neutron. So this is possible, but it's rather rare. All right, so let's look at the alpha decay first. As I said, we start from a rather large, heavy nuclei, and it seems possible for it to spit out helium or an alpha particle. So the first thing the view we want to have here is of the potential in which the alpha particle sits. So the alpha particle sees a really deep well of the nuclear potential, and it also sees then this boundary here, this barrier of the Coulomb potential. So for the alpha particle to be emitted, it needs to break through this Coulomb potential here. And you can calculate the likelihood using quantum mechanics, the tunneling likelihood, in order to figure out how stable an individual particle is. Here, I just wanted to show you something. This plot here shows you the lifetime of an unstable nuclei for various sorts as a function of the energy. And what you see here is this very strong energy dependence. This is the logarithmic plot. And what you see is the lifetime seems to be rather short when the emitted particle has a lot of energy. And that can be explained by this plot here very easily. In order for this particle, the energy of this particle when it goes here is dependent on where this particle sits in this potential, right? So particles which sit at very high values here will have a high likelihood to tunnel through this barrier and therefore a short lifetime. Hence, this particle has a lot of energy after it's being emitted. So we see lifetimes in the range of 10 nanoseconds to 10 to the 17 years for some examples. So there's this huge variation depending on where the alpha particle sits in this potential. We can have a discussion of the energetics involved, and we use our very same formula for the binding energy. So you write this down here, including your your helium here, and then just figuring out what are the contribution of the individual terms. And since we observe experimentally alpha decays only for heavy particle, in this discussion here we can assume that Z is approximately 0.41 times the mass number. And so the energy of the emitted alpha particle for this to be able to occur is has to be positive. And so we find this to be possible for A values starting from about 150. Experimentally, we observe this to start happening at about 200. All right, the next sort we want to discuss is beta decay. So this is shown in this diagram here, where, starting from carbon-14 decays, for example. Carbon-14, you will see this in the next recitation, is a very useful probe in order to date living things and date when they were not living anymore. And we will discuss why and how you can actually do this. But for now, carbon-14 can decay via beta decay. And what you find is nitrogen, an anti-electron, and an electron. This is a beta decay or beta minus decay. And using our particle physics discussion, we can easily understand this. A neutron is transformed into a proton via electroweak processes with a W. The electron comes out, the anti-neutrino comes out. And similarly, we can look at carbon-10 here into a boron with a neutrino and a positron. And again, here we have a W plus in the decay. So now we can again use our binding energy in order to understand this. So what we want to do here for constant mass numbers, we want to plot the binding energy for the individual atoms or nuclei. And so if you do this for odd A, right, those is where the pairing term doesn't contribute, you find this nice quadratic term, and you can find beta decays in each of those instances here. For A even, we have the question whether or not Z is odd or N is odd. Oh, sorry, Z and N are odd or Z and N are even. So you have two quadratic functions here, and you find the beta decay between one and the other. And so that's interesting. You find those decay chains based on where you start in the chain. You have the possibility to go back and forth. And because of the even and odd pattern, the lifetime of the decay can vary quite tremendously between those individual states. Last but not least, electron capture. If you have a very massive nuclei, an atom, and the electrons, thinking about a cloud around this, some of the electrons can come very, very close and be captured into the nuclei. And you find this here. The time direction goes up. The proton captures via the weak interaction. The electron becomes a neutron and emits a neutrino. And an example is the electron capture of krypton into boron. All right, so we start to get some sort of understanding of nuclear decays. We find this value of stability here. We find in a large range for lower numbers of Z, beta decays. For higher numbers of Z, we find beta plus decays. And for very heavy nuclei, we find alpha decays. Proton decays are seen at the very boundary here, and nuclear fission processes where the nuclei spontaneously breaks up. We haven't discussed in detail, but you can think about them very similarly to the alpha decay. As you already kind of probably saw from the discussion of the beta decay, it's possible to have rather long decay chains. So you start from a radioactive nuclei, which then decays and decays and decays and decays in those kind of chains. So this is, two examples here, the thorium chain and the uranium chain, creating all kinds of other new elements. And on the uranium chain, it's very interesting to say uranium, is part of our core. If you build a house and you build if you build the foundation with concrete, you probably have some uranium in there, which then in this decay chain generates radium. And therefore, if you build a house with a concrete, you want to have a measure to get rid of the radium, which is just floating around there. All right, so this is it for now. We continue the discussion with more detailed understanding or detailed discussion on how those decay processes are possible and what we can learn from them.